All right, AP Chemistry, page 89. We're still in electrochem, and we are still in what would be called electrolytic cells, or the idea that we're not letting a battery run and produce electricity, we're putting electricity in. So it's important to realize electricity is going in to push a reaction forward, or to push a reaction that is normally not spontaneous. So we have to put the energy in so that the reaction will go the direction we want it to go, which is the way it doesn't want to go. In other words, we're recharging a battery here. So fancy name for a battery is electrochemical cell. Fancy name for going backwards or charging a battery would be electrolytic or electrolysis. And so what we need to look at, and this is just going to be one page of notes, because I'm remembering I should turn off my video because that seems to help the recordings. Because things are going to get a bit complicated in this one lesson. If you take an early look at these three equations, here, here, and here, they're easy to mix up. All three have water. Two of them have hydroxide. Two of them have oxygen. They all have two electrons, which is convenient. So two electrons, two electrons, two electrons. And we've got hydrogen here, hydrogen ion here. So it's so easy to mix these three up, which is why I'm only doing one page on this lesson. So putting electricity in, we want to see what's going to happen. So first, notice I have separated the cathode from the anode. And again, at the cathode, it's going to be reduction. At the anode, it will be oxidation. And also, please notice the notes helping you organize things. There are 3 bullets for the cathode. 1, 2, 3. And there are 3 bullets for the anode. 1, 2, 3. They're also in the same order. So if you look back at it, we've got cation, anion. That kind of suggests why the cathode's called the cathode and the anion's called the anode. That's weird. Next, we have H plus and hydroxide in the second bullet. And then finally, we have water in the third bullet and water in the third bullet. This has been very carefully organized to help you keep this straight. So let's go through the options. Start with the cathode, where we have reduction. Well, the most obvious reduction is to take a metal ion, so I'm on the first bullet, like copper plus 2, let it gain some electrons to make copper metal. So this would be copper solid, and this one here would be copper aqueous. So we're actually making copper metal from copper ions. And this is very common for the transition metals, as it says. Another option, which would happen if you're in an acid, especially a strong acid, is a strong acid has, I'm now looking at the second bullet, has a lot of H+. So the H+ can be reduced. And if you give H+ electrons, it becomes H2 gas. So that's something to be aware of. And that would look like this: H+ plus an electron, forming H2 gas. The H+ would be aqueous. And if we go to balance this, you'd realize, oh, I've got to put a 2 here and I've got to put a 2 here. Something like that. Finally, there are certain things that do not want to be reduced. They are stubborn and they say, don't reduce me. I'm not going to reduce unless there's no other possibility. And those are group 1, group 2, and aluminum, when they're in water, by the way. If they're not in water, you can reduce them. But we're assuming everything's in water right now. So in this case, if these things are in water, the water molecule will reduce instead. And the equation that it looks like is water plus electrons, so reduction. The electrons go to the hydrogen atoms to make H2 gas, similar to what they did in the second bullet, and you're left with 2 hydroxides. Now, some notes that I've made here is if you analyze the sodium ion, let's say we have sodium in water. If you were to reduce it, you would be making sodium metal solid, which of course, group 1, including sodium, is famous for being highly reactive with water. So let's say you actually did this. Let's say it did happen. Well, the sodium would immediately react with the water to turn back into the sodium ions, and it would make hydrogen gas, which is why it explodes if you do it too much of it, and you also make some hydroxide. And I have that written right here to help explain why that happens, if you want to study it in more detail, and you should. In other words, when you have group 1 ions, group 2 ions, and aluminum ions in water, the water will reduce first before those ones. All right, so now let's back up a little bit, get rid of all this stuff, and realize we just took care of the cathode. Now we have to do the anode. So for the anode, where we have oxidation, the most obvious thing is to take some sort of anion, like chloride, and take some electrons from it. If you take some electrons from chloride, you could, which is diatomic, and other things like that. Another option is if you're in a strong base, you've got a lot of hydroxide ions, and those hydroxide ions can lose some electrons and become oxygen. And this reaction looks like this one here. Hydroxide becomes oxygen and water, and these electrons are available to be gained by something else that's present. In this case, let's see. It's not so much that anybody is losing the electrons, any individual atom, but I suppose if you had to say who's the victim here, who's losing, it'd be the hydrogen in hydroxide, because it ends up turning into H2O, in which the oxygen is going to hog those electrons in the polar covalent bonds. And the third option is that water, if these 3 things are in water, nitrate, sulfate, or fluoride, water will lose electrons before those 3. So first, let's look at why that's the case. Well, if you look at the oxidation number of nitrogen and nitrate, you should get a +5. That's a high positive oxidation number. It's not going to want to lose instead water does. Likewise, in sulfate, sulfur's +6. It's not going to lose more electrons. And even though F- is a negative ion, it's fluorine, which is known for being so electronegative. It is not going to let its electrons go easily. So in this case, even though it is a negative ion, it's not going to let it go. And so its high electronegativity will win out and water will lose electrons. Instead, it looks like this. Water loses 2 electrons, and you end up with oxygen and H+. So what we're going to look at now are some examples. And as we go through these examples, what I encourage you to do is start with what's given and see if you can figure out which of these 3 things is going to happen. Is it going to be 1, 2, or 3 for the cathode? And it can only be 1. And will it be 1, 2, or 3 for the anode? So let's say we do electrolysis, putting electricity in hydrochloric acid. In this case, it would be the second bullet. H+ will gain electrons to form H2 gas at the cathode, because that is your reduction. And the 2Cl- would lose electrons to become Cl2 and 2 electrons. It just happens to work out to be 2 electrons, so that's convenient. So balancing is easy. And if you add the 2 half equations at the 2 electrodes, you would get the overall equation as written here. And if you look at this, essentially we're saying hydrochloric acid, if you put electricity into it, you make a flammable gas and a toxic gas. So this would be a bad demonstration. If I did this, this would be irresponsible. The H2 isn't that big a deal. I can handle the flammable gas, but the formation of this chlorine gas, that would not be good for us to breathe. So I'm not going to do that. Next example. Electrolysis of copper sulfate. This is a more traditional one that you might actually see. There's probably videos on YouTube of this, I imagine. In this case, the copper ion will gain electrons. So that's its reduction at the cathode, metal. And I usually do this demonstration in class to show you. And at the anode, the sulfate will not get oxidized. It's one of those ones that water gets oxidized instead. It'll make oxygen gas. So if you were to watch this, you'd see oxygen bubbles coming out. And it makes some hydrogen ions. So this is a good demonstration, but it is bad for the environment. This on a huge scale. Like if you make copper this way for some sort of industrial purpose, this is not good for the environment, because if you look at the overall reaction, we have copper ions becoming copper metal. That's fine. We're using some water. Okay, that's fine. We're making oxygen. That's wonderful, but we're making hydrogen ions. So if you do this and do it on a huge scale, you have to deal with this acidic waste. And unfortunately, in the past, companies have not dealt with it responsibly. And that's one of the reasons why there is the EPA, the Environmental Protection Agency, is to make sure that they're responsible with this stuff and they don't keep ruining the environment. And a third example, electrolysis. Let's see, let's do blue this time. Electrolysis of sodium hydroxide. Well, sodium ions are not going to be reduced in water, so water will get reduced, gain electrons, making hydrogen gas and hydroxide. At the anode, hydroxide, that's fine. Hydroxide can be oxidized and it makes oxygen, water, and 2 electrons. And it just works out that all of these examples have 2 electrons, and that's just convenient for us. This one's interesting because the overall reaction, when you add everything up, 2 hydroxides are consumed, but 2 hydroxides are produced. So it's weird. You're making hydroxide, but you're actually not increasing the amount of hydroxide because you're also consuming it at the same rate. And then just add everything else up, and you get that ultimately all that's happening overall is water is being turned into oxygen and hydrogen. This would be a okay demonstration because at least nothing's toxic, but you'd have to be careful because you'd be making a flammable gas, H2, things burn O2 in exactly the right stoichiometry to cause an explosion. So it just have to be done in a careful environment. Now I made a note here. The concentration of sodium hydroxide goes up. So at first, this shouldn't make sense. If you look at the overall reaction here, you should think, I don't see sodium hydroxide at all. How is it that sodium hydroxide is going up? So I'm going to let you think about that, and we'll talk about that in class. But there is a reason why the concentration of sodium hydroxide goes up. And then in class, we'll do the electrolysis of water lab, which I'll do that as a demonstration lab because of equipment and danger. And I will cover all this stuff during the lab. So that actually finishes this one. Nice, only 1 page.